Welcome to ISAT430 Materials and Manufacturing Processes. This is lecture 3, Metals and Ceramics. So in this lecture, we'll have two major topics. First, I want to talk about the metals, and then next, I want to talk about ceramics. In metals, mainly I want to discuss different alloys and also ferrous metals versus non-ferrous metals. In ceramics, I want to discuss structure and properties of ceramics, traditional ceramics, and also new ceramics. Also, glass as a special type of ceramics all will be discussed. Lastly, we're going to talk about some other elements related to ceramics, for example, carbon and boron, and also silicon. All right, first, metals. So metal usually have some very common characteristics. For example, ductility, malleability, and luster, and also high electrical and thermal conductivity is all related to its crystalline structure. And usually the starting form of the manufacturing process of a metal is cast metal or wrought metal or some powder metal. So casting has been a really common process before some other machining process or follow-up machining processes. And powder metal, if we are making some of the sometimes you can use powder and compress it and to become a solid parts, or sometimes you can use laser to have some kind of heat bonding of the powder to form different parts. Two major categories of metals: ferrous metals versus non-ferrous metals. So the difference is that ferrous metal is based on iron. If there's some iron element, means there's are ferrous metals. If there's no iron element, means they are non-ferrous metals. So this is a table about metallic elements. All different kind of metallic elements. You can see the gravity and also the melting temperature as well as Young's modulus. So something you want to pay attention to is that among all these metals, you can see there are some very light metals. For example, like magnesium, tin, right, and zinc. Right, so these are relatively a little bit light metals. So for this, the application of those can be some lightweight applications, for example, aerospace or some other industries. And also there are some really high temperature, high melting temperature metals. For example, let's see, tungsten, right, and molybdenum, and also platinum, and also our iron and titanium, right. So these metals, because they have higher melting temperature, you can use those kind of elements or these metals in the industrial environments where high temperature is required. For example, cutting tools, right? Cutting tools, or some heat treatment facilities, or some equipment that is related to incineration or some other burning environments. All right, next let's look at alloys and phase diagrams. The first alloy, the definition of alloy is a metal composed of two or more elements, at least one of which is metallic, right? So this is called alloy. And usually there are two different categories of alloys. One is a solid solution that are in intermediate phases. Later, we're going to talk about what they are. And so for the phase, the definition of a phase is that it's a mass of material with the same crystal lattice structure. So if you put the metal under microscope, you will see there are different structures. Sometimes you can see different structures, of the metal. So the reason with that is because it's not pure. There are also some other elements. It really depends on how much it can be dissolved of the other element. If it exceeds a certain limit, then we'll form another structure next to it. So that's why there are different phases. All right. So the solid solution means the material can be dissolved in the main element. For example, this is the zinc in copper, right? So copper is the base material, while zinc is the second element. So that's why so zinc, as you can see, the zinc molecules can replace some of the copper molecules and then form the same structure. Well, another type is interstitial solid solution. So it means that some of the other elements will be filling the gaps of those molecules of the base material. For example, like this one. So it has carbon actually filling the gaps of the iron material structure. And steel will be one of the examples for this kind of a solution. All right, so intermediate phase means for a second element or some other element, there's always a limitation or a limit, right, for dissolving another element. So this is why if you exceed it, it will form another phase, a second phase. So this is what happens. And now let's look at this. This diagram is called phase diagram. So the phase diagram means it has an element, right? What kind of element? A and B, and also has a temperature. So with the composition of the elements changes, and also the temperature changes, the structure actually will be different. And this diagram will show that at a certain point, at a certain composition and also at a certain temperature, what is that phase? So this what's the structure? So this is what the phase diagram I'm going to tell you. For example, in this diagram, when we are in this area, right? For example, when we are in this area, it's mostly A element with a little bit of B element. And in this case, when the temperature goes up, it will stay in this alpha phase, right? Well, in this alpha phase means this is the alpha structure of the material. Well, let's look at another case. For example, in this point, right? In this point, now we have this composition, right? Let's call it A1B1, right? This composition at this temperature, let's call it T1. All right, in this case, what happens that for the material or the solution you have is composed of alpha, right? Alpha phase and also A and BN phase. So the A1B1 phase. Right, A1B1 phase. You will see two different structures within in this material under microscope. If the temperatures keep goes, what happens that it will keep going up, and then reaches a point. So this point is a eutectic point. Eutectic point means A will not go through phases like this and this. Right, see, this phase means it's a mixture of both liquid and solid materials, right? Same with here, it's mixed of both liquid and solid material. Well, at this point, what happens is there's in this point means the solid and liquid material will exist at the same time. There's no transition, right? There's no transition. So this is what happens with eutectic point. All right, in this case, if we keep increasing temperature, what happens is that it will once the temperature goes up to a certain point, let's take the Tn, and it goes up here, it will become all liquid. So basically, this is what this phase diagram I'm going to tell you about the material structures at different phases at a different temperature and also composition. You can see this is the structures under a microscope. All right, so this is another example. So this is copper and nickel alloy system. You can see what happens here, and so under this line, for example, under this line is all solid, right? It's all solid solution. Well, above this line, there is a place that is all liquid plus solid. This liquid plus solid. If you want to know how much liquid and how much solid, there is a way. So which is this equation and this equation. If you want to calculate, so for example, we are at the point C, right? We are at the point C, which means we're at 50% of nickel and 50% of copper. Well, when it is at the temperature of this temperature, which is 1,260 degrees Celsius degrees, and you can draw a line here with L and S. Right? If you want to calculate the liquid phase, we're going to use CS, right? Which is this part, C from C to S, divided by CS plus CL. This is the whole segment length. Same, if you want to calculate the solid phase, then this is the rest part of that. So this is how you can use this to calculate the percentage or portion of solid and liquid in this material. This is another example. This another example is lead with tin, right? Lead with tin. So this is tin and lead, for example, is alpha phase here. When we are at this, maybe the 20%, less than 20% of tin in lead, and if we keep increasing the temperature, most of the time actually it's at alpha phase, right? But of course, there are some cases is in this phase. In this phase, the structure will be both alpha and beta, right? Both alpha and beta. And the eutectic point is here. When the percentage of tin is 61%, 9%, and when it's at the temperature of 183.1 degree Celsius, then it will form this kind of eutectic point, right? Transition or at the same time, both the solid and liquid will exist. You can see the two figures here. These are the optical micrographs of the tin lead structures under two different conditions. You can see how different you are. They're under the same scale. All right, next let's talk a little bit about ferrous metals. So ferrous metals mostly it's iron and steel. It's just different kind of iron and steel, and so there are common alloys of iron and carbon are steel and cast iron. So just remember, for steel, usually the carbon percentage is less than 2.14, right? For the cast iron, it's about bigger than 2.14 and smaller than 4%. So this is about cast iron. The difference is that what is the percentage of carbon in iron. First, let's look at this iron carbon phase diagram. This diagram is a very important diagram because for the traditional heat treatment of steel and iron, cast iron, they use this phase diagram as a guide to process the metals. And you can see the difference between in two different phases, ferrite and austenite. So ferrite and austenite, there are two different phases of the carbon iron material. For example, alpha phase will be body-centered cubic. Right, we talk about different crystalline structures. This is body-centered cubic, and gamma will be austenite. Right, so gamma, this is gamma, this is gamma, this is gamma. Will be a face-centered cubic. While theta is also a theta phase, which is here, there. That is also body-centered cubic. So what happens here is when the carbon in the iron is at a certain percent, then you can use this diagram to see what kind of a phase is at, for this material is at a certain temperature. For example, if we are here and we keep go up, right? At first we will have a mixed phase of this solid, and if it keep going up, we'll have alpha and gamma, right? Both the ferrite and the austenite structures. And if we keep increasing the material, you can increase the temperature, we'll get into this gamma, which is austenite structure. And usually what happens is that people will rapidly cool the material, right? Cool the material so that it will still keep this gamma structure at a normal temperature, right? At a room temperature. And then in this case, what happens is that you will achieve higher strength or higher stiffness of the material in order to get certain properties of the of the material you want to get. So this is how the iron carbon phase diagram will help you as a guide to process or heat treatment of the metals. So for the iron and the steel production, usually it starts with iron ores and also some other raw materials. You can see the 50. This hematite has a 50 to 70% of iron. Magnetite has this, and also the coke and limestone. These are all the raw materials we get from the natures. And this is a production process for general production process for iron and steel. Usually it starts with a pig iron with some impurities, right? Impurities can be silicon or and also some other elements. And there are some ways to get rid of those elements. For example, we can use oxygen, right, to let them have some reactions and then get some slags, right? It will be those impurities will be get rid of. And so general process is that the pig iron will be carried out to the top, and then get into this get into this shell, right? And these are different layers of iron ore, coke, and limestone. So these are raw materials, and then it has a really high heat in this environment. And there's the hot blast air getting to this shell, right? So the air will include the oxygen, right? The oxygen, and oxygen will react with carbon to form carbon monoxide, and then to have some reactions. For example, this kind of reactions to get pure iron. And so here you will see some of the slags will appear, and also the iron will be flowing out to a ladle car, right? This is a hot iron to ladle car. So basically, this is how the general process for making iron and steel. And there are two different major processes for making steel. So one is BOF, so basic oxygen furnace, and the other one is electric arc furnace. So let's first start with the basic oxygen furnace. So for the basic oxygen furnace, so basically you put a pig iron into this furnace, right? Usually, the raw materials will be pig iron, as well as about 30% of steel scrap. So some recycled steel can be added in there to for production. And also you need to make sure there are some oxygen to get into this furnace so that can have some reactions. For example, the oxygen can be reacted to carbon, to silicon, and some other elements to get rid of those impurities. Then the molten steel will be at the very bottom. Then this molten steel can be carried to some other places for follow-up processes. Well, for the electric arc furnace, the difference is that for the electric arc furnace, we're gonna use electrodes, right? Electrodes to heat up the environment, right? Electrodes to heat up the environment. Well, for a furnace, there are different ways to heat up this furnace, but it's more traditional ones. But this one, but for electric arc furnace, we use electric arc to heat up the environment, and all the rest will be about similar. You see the molten steel are at the bottom here, and also the slags will come out from here, and these are the electrodes. And the molten metal will be poured to this ladle, right? Molten metal will be poured here. So this method usually has a better quality of steel and also higher cost. The reason is because it is much easier to control the electrodes, the powers, and also the temperature of the reaction environment. Compared to the oxygen furnace, it's a little bit hard to control it. And you have to, that's why sometimes you're probably gonna get higher quality of steel with electric arc furnace. And after we got this molten iron or steel, what we're gonna do is we're gonna put them into a follow-up process, which is to cast the molten metal into different shapes. Right, shapes can be ingots or some rolls or sheets. Right. So this is a continuous casting. So this will be ingots, and then you got some mold, right, and then cast it into different shapes. And if it is continuous, then you will also need to have a cooling period, so cooling process. Usually people use water to cool it down. Then in order to make it into a certain shape, you'll need to have different rules, right? Bending rules, many different shapes. And there are two videos about steel production and iron steel production. Please watch those videos first, and then we can continue our slides. Okay, I'll just let's assume you already watched the video. Now let's look at steel. We talk about the production process. Now let's look at different kind of steels. So as we mentioned before, the steel usually have the carbon content of 0.02% to about 2.11 or 2.14% of carbon. And of course, sometimes we can add some other ingredients in order to improve its properties. For example, magnesium, chromium, nickel, and molybdenum. Later, we're going to talk about what kind of characteristics they have, and how they can strengthen the properties of the steels. So different kind of steels, plain carbon steel, low alloy steel, stainless steel, tool steel, and specialty steel. These are all can be used in different industrial applications. Let's start with plain carbon steel. So for plain carbon steel, mainly it's of course is steel, but it also have some alloy ingredients. So main alloy ingredients for this is magnesium. And the phase diagram will be more of a ferrite and now cementite, right? Ferrite and cementite structures. And there's a standard for naming the plain carbon steel, so which starts with 1000 something, right? So 10 means it's a plain carbon steel, and XX indicates what percent of carbon. For example, if it's 0.2% of carbon, then we're going to name it as 1020. So this is how you can use those numbers to interpret what kind of percentage of carbon in the plain carbon steel. Right? Alright, yeah, within this kind of plain carbon steel, you can also classify them into three major categories: the low carbon steel, medium carbon steel, and now high carbon steel. For low carbon steel, usually that's about 0.2% of carbon. It's also most widely used in steel in industry, and applications can be some car sheet metals and railroad metals, rails, and also plate sheet for different fabrications. And the medium carbon steel are the steel with carbon percentage from 0.2% to 0.5%. Usually, because of the carbon increases, so actually the strength and also increases with more carbon. So this kind of plain carbon steel can be used in higher in environments that requires higher strength, like machinery components and also engine parts. Well, if the carbon percentage is bigger than 0.5%, then it has even higher stiffness hardness, and then it can be used in applications that require those properties, like springs, cutting tools, blades, wear resistance parts. Right. So basically, increased carbon content strengthens and hardens the steel, but ductility actually reduced. All right. For low alloy steels, so other than carbon, they also contain some other alloy elements. So chromium, magnesium, molybdenum, nickel, and vanadium. So all chromium, it has a special other than strength, good strength and hardness. It has a special property that is wear resistance, right? So if you want to have the steel have better wear resistance, then you probably want to have more chromium in it, right? For other materials, like magnesium, molybdenum, usually it's and also some other elements. Usually, if you increase those kind of elements, actually it will perform better in strength and hardness. All right, for low alloy steels, usually because it does not really contain a lot of alloy, so the properties compared to standard alloy steels, actually it's not really high. So that's why heat treatment is often required. And for the naming of those, with different ingredients or different alloy elements, they also have different names. For example, 1300, that is the magnesium steel, 2000, that is nickel steel, 31, that's the nickel chrome steel, and 40, that molybdenum steel. So you can use all these different numbers to name and interpret what kind of alloy steel it is. Well, stainless steel, from this name, we use stainless steel a lot in our lives. So stainless means it's corrosion resistance, right? We mentioned about chromium from the prior slides. Chromium, it has good wear resistance, so that's why in stainless steel it has really high percentage of chromium in it, usually about 15% chromium. So that's why it can form a thin oxide film, at the surface in order to prevent that kind of a surface. Different groups of stainless steel. Usually, the stainless steel usually have the kind of 3-digit numbers, right? Compared to the 4-digit numbers of other steels, right? And also, groups can be austenite stainless steel, ferritic stainless steel, and martensitic stainless steel. Another type is a tool steel. So because in some of the extreme or higher requirement, higher for either temperature or strength or load, right? It requires the metal to be very higher performance in order to to process some other metals or process some other materials. That's why people have created those tool steel that have more alloys into the steel, so they can enhance its properties. For example, hardenability, the distortion, hot hardness, toughness. And also abrasive resistance, right? So some of the applications for tool steels, it can be the die, right? It can be the cold work tool steel, for example, making the dies of sheet metal processing, or hot working tool steels, like in hot working dies, in forging, extrusion, and die casting. And some other applications can be shock resistance tool steels, like punching, shearing, and bending processes, right? And mold steels to make some molds for plastic and rubbers, and also some alloy steels for some other applications. Then another major type of ferrous metals is cast iron. So the cast iron, we mentioned that for steel it's less than 2% or less than 2.1%. While cast iron, usually that's the carbon content has bigger than 2.1% and less than 4%. And also have silicon component that is between 1% to 3%. And some of the typical cast iron are gray cast iron, ductile iron, white cast iron, and malleable iron. You can see some of the pictures about cast iron. This is comparison of cast iron versus steel. You can see steel has better corrosion resistance. And so this is what it looks when you have the silicon and carbon, where this kind of steel is at, and also gray cast iron. This is all because of the carbon percentage change. If its carbon percentage is less than 2.1%, then that's steel. If it's bigger than that, they will have white cast iron and also gray cast iron. After we talk about ferrous metals, now let's look at different non-ferrous metals. For non-ferrous metals, some of the common ones are aluminum, copper, magnesium, nickel, titanium, zinc, and of course some alloys. Okay. So the reason we're gonna use different metals is because different metal elements is because they all have different properties, that they're unique behaviors. So that's why I'm gonna use it in different applications. Starting from aluminum. So processing of aluminum actually has a long history. It started from the late 1800s, and at the very beginning, the process was not very mature. Actually, aluminum used to be a very expensive element or material that is in people's lives. Then later, when the process get more mature, mass production of aluminum, or sometimes you can call it aluminium, it gets more available to people. Then the cost reduces, and it's more available to different applications. So the original material for making aluminum is from aluminum ore, and that's the bauxite. It contains of this element, and this is a general process. How do you make aluminum? And you should watch this video, right? You should watch this video when we are going through the slides. So the typical properties for aluminum is that first it's a light, it's relatively light compared to some other metals, right? It's a light metal, so that's why it can be used in some applications that requires not really heavy environments, and also it's a resistance to corrosion, right? It has good ductility. And also it has high electrical and thermal conductivity. Okay. Next metal is magnesium. So magnesium is a very light metal, right? It's even lighter than aluminum, and usually we get that from seawater, right? Get that from seawater. And the typical property for the magnesium is that it's very soft, and it lacks of strength. So that's why its strength to weight ratio is a good advantage. So remember this term, strength to weight ratio, means it's the material is light, but it has really good strength, right? So that's why in aerospace or in some cars or missile products, usually it requires you to use the materials that with really good strength to weight ratio. Another type of strength to weight ratio is titanium, right? You can tell why titanium is usually used in aerospace. We're gonna get into titanium in a minute. All right. Another metal is copper. So copper is also a very common material we see in our lives. It has a reddish pink color. You can see the reddish pink color, and also low electrical resistivity. So it has really good conductivity. That's why it has been used a lot in wires, right? Used in wires. Also, it has very good corrosion resistance. but its strength and hardness are relatively low. Something to mention that from using copper as a base material, and if you add zinc and lead in it, you will create two different common materials. One is the brass and bronze, right? One is brass and bronze. So this is a comparison of those three materials. In the middle, it's copper. This is brass. This is the bronze. You can tell from its color, right? You can tell from its color. Because brass has some kind of gold color, so actually brass has been used a lot in applications that requires a good aesthetic look for products or different places. Well, another metal is nickel and its alloys, and nickel also have really good corrosion resistance, so that's why it has been used a lot in coins, right? In coins, right? It has a high temperature property and also good Youngster modulus. You can see with different other elements. And nickel as a base material, people created different kind of coins. Next, titanium. We mentioned about titanium. Mentioned that it has a really good weight strength to weight ratio, so it's been used in aerospace applications. And its density is actually between aluminum and iron, so which means it's a little bit heavier than aluminum, and it's lighter than iron. And some of the properties about titanium is that it has a low thermal expansion, so which means if if it is working in a very high temperature environment, it's likely that it's hard to deform, right? So it's also stiffer and stronger than aluminum. Another property of the titanium is biocompatible, so which means that you can use titanium as implant materials. So that's why it also has been used in medical care. The next is zinc. So zinc has a really low, zinc and lead and tin, those kind of three materials, usually they have very low melting temperatures. So that's why it has been used a lot in casting, right? In casting processes. Zinc also have this corrosion protection. A very common steel you're probably gonna see is the galvanized steel. So this is kind of steel is a steel that is coated with zinc, right? So galvanized steel means it's a steel that is coated with zinc. And for lead and tin, usually has been used a lot in soldering process. Because of they both have very low melting temperatures, and also it's a dense metal with very low strength, low hardness, but with high ductility. So that's why it's been used a lot in electrical components. But because lead has certain toxic impact on human health. And in recent years or in recent decades, actually the government has been give a lot of regulations on limiting lead use in electrical components. Some other non-ferrous metals are, for example, molybdenum and tungsten. So both of them can be used in refractory environments because they have really high melting temperature, right? It also has really good stiff and hardness strong materials. It's being used a lot in tools, right? In tool materials or alloy materials. Another group of metals, these are the precious metals. So precious metals, they are very noble, so they're very stable in chemistry in reactions. They do not usually react with other elements in certain environments. So that's why it's very stable, inert, and because it's limited amount, right? And also aesthetically look, it has been used a lot in jewelry industries, right? There's some silver, gold, and platinum. So silver, gold, and platinum also can be used in some dental work, right? As implants, dental work. Lastly, there are some kind of super alloys. So the super alloys, these are some kind of alloys that are created for applications that requires very extreme working conditions. For example, the temperature in around 1100 degrees Celsius, right? Or requires really high load. So those kind of applications are, for example, like gas turbine, jet rocket engines, steam turbines, and nuclear power plants. And three different groups of the alloys are commonly used: iron-based alloys, nickel-based alloys, and cobalt-based alloys. All right, next, after we talk about metals, now let's look at different ceramics. First, ceramics is actually being widely used in our life, and also probably even longer has a longer history since from ancient times. And the general properties of ceramics are they have really high hardness and stiffness. So you want to compare this with brittle, right? Yes, they have really high hardness and stiffness, but it is very easy to fracture, right? It's very easy to fracture. And ceramics also have really good electrical and thermal insulation. You can see some of the ceramics you have at home, right? They do not conduct electricity. So that's why because what? Because their bondings. Usually, ceramics have covalent bondings, right? Not ionic or metallic bondings. So that's why it's very stable, right? Their bondings are stable and it do not conduct electricity. Also, they are chemical stable. So that's why sometimes a lot of times they can be used as containers in ceramics, right? Because they cannot react. Usually, they do not react with different chemicals. High melting temperature. So bondings, usually the covalent bonding and ionic bondings are stronger than metallic bonding metals. So that's why they have high hardness and also stiffness. But they do not conduct electricity very much. Strong bondings that's why they have high melting temperature. Most ceramics actually have crystalline structure, but there's one exception, that is the glass, right? So some of the ceramics, for example, the glass, have the amorphous structure. So mechanical properties of ceramics will be usually they're rigid and brittle and so for ceramics, they do not really deform. They just fracture, right? They're just fractures. So they have a low tensile strength and toughness. Good tensile strength means what? Good tensile strength means they can actually deform and then tolerate those kind of deformation, and then later they fractures. But bad tensile strength means they can easily fracture. Right? They do not deform. All right. Some other physical properties of those: they are lighter than metals and heavier than polymers, and the melting temperature are usually higher than most of the metals. And thermal expansion coefficients are somewhat really less for metals. Means that they do not really expand or deform with a change of structure. With really high temperatures. And for the raw materials for ceramics are usually one is silicates, silica, and also alumina. So these are the typical raw materials for making ceramic parts. Let's look at some traditional ones. Traditional ceramics, for example, like potteries and also tableware. Usually it's a clay, right? The clay combined with other minerals, and then they can make them fire them first. Fire them, and then you can get a finished products after cooling down for a period of time. Then you can make some nice potteries and the tableware, for example, china, the stoneware, and also earthware. And some other ceramic products, for example, the bricks. Brick is another type of, and tiles. These are another type of ceramic products, and also some refractories, and often in the form of bricks. To make some furnaces, right? Usually furnaces need to tolerate high temperature. And some example of those ceramic products were like alumina, and magnesium oxide, and calcium oxide. And also another type is another type of product that you can be used in abrasives, right? In abrasives, like for example, grinding process, grinding wheels. They can have some of the abrasive material, abrasives on the tools, because they have really good high hardness, right? Also, there are some kind of new ceramics. So new ceramics usually they are designed for for environments or working environment with high and very special requirements. There are three major categories: the oxides, carbides, and nitride. First, oxide. So oxide, the most common or important oxide is alumina. So usually this oxide have really strength and toughness of that has been substantially improved. It has a really good hardness and low thermal conductivity and good corrosion resistance. And for this, it has been used a lot in implants or the dental industry. For example, like this, right? For example, implants, right? Because they can be used as bell ceramics, right? Artificial bones or teeth. And also because they have really good thermal expansion, very low thermal expansion, and can work in a very extreme material environments, and it can be used as cutting tool inserts, right? Cutting tool inserts, because they have really good hardness and thermal expansion, low thermal expansion. And so when a tool is cutting materials, it actually usually is at a very high temperature at the contact point. Of course, you can use it as refractory bricks, right, to make furnaces. Another type of new ceramics are carbides. So carbides can be tungsten carbide, silicon carbide. Usually they're similar as as oxides. Applications usually they require really high strength. Resistance, heat resistance, and also good hardness. So tungsten carbide is also a very common cutting tool material. So if you go to some different websites, you want to buy some cutting tools, you will see different carbides, or sometimes it's the high speed steel, tungsten carbide, or boron carbide, or different kind of materials. So the nitrides are also nitrides usually have hard and brittle, but their high temperature is very their melting temperature is really high, but it's not as high as carbides. Okay. There are silicon nitride, boron nitride, and also titanium nitride. So these are for example, silicon nitride, it has really thermal expansion, resistant corrosion, and gas turbine, rocket engine, and some applications that require really extreme conditions. You can use those kind of materials, new ceramics and nitrides. Next, glass. So when we're talking about glass, actually there are two different concepts. One is glass. We call it as the physical state, right? Physical state. When there's an insufficient time is allowed during cooling from a molten condition for crystalline structure to form, right? So if you quickly cool the molten material, and it actually will form a amorphous structure if there's an insufficient time for the cooling process. And for that, you will see different properties later when look at. Well, as a type of ceramic, it is also when we are talking about glass, mainly we are talking about the glass we see in our lives, right? It's a type of ceramic. It's an inorganic, non-metallic compound that cools a rigid condition without crystallizing. Different glass products. There are window glass, containers, label glass, and also optical glass. Let's look at different products. All right, so glass. Usually its grain size is significantly smaller than conventional ceramics, which makes the glass ceramics much stronger than the glasses from which they're made, right? And because they have the crystalline structure, glass ceramics are usually opaque, but not clear, right? Not clear like this. Glass ceramics usually have really high strength, absence of porosity, and also low thermal expansion. So that's why a lot of times we can use those glass ceramics in in the microwave or in cooking, right? As cooking wares or heat exchangers, because they have a high resistance to thermal shock. Well, some other elements related to ceramics include the carbon, silicon, and also boron. So the carbon, there are two different alternative forms of engineering and commercial importance. This is graphite and also diamond. Now let's look at carbon. So graphite. Graphite it's a form of carbon with a high content of crystalline carbon in a form of different in all layers. They are all layer by layer, and bonding between the layers in layers is covalent and strong. right? Atoms in layer is covalent and strong, but parallel layer is kind of a little bit loose because they are using what van der Waals forces, right? The van der Waals forces are the forces between atoms, molecules. And if it is a powder, usually you can use it as a lubricant. And if it is a fiber, then it actually forms a very high strength structure material. For example, carbon fiber, right? Well, diamond. Well, we know that diamond is actually the hardest material in the world, and it actually is pure carbon, right? It's a carbon with cubic crystalline structure with covalent bonding between atoms for high hardness. And diamond has been used a lot in cutting tools as well as also the grinding wheels. Remember when we were doing lab 2 about tensile test and hardness test. In the hardness test, we have a diamond, right? We have a diamond indenter for the test machine. And silicon, so silicon is a very special element because it can perform differently under different temperatures, and especially for conductivity. So that's why it's being used a lot in electronics industry as a semiconductor. But the silicon actually it has really abundant amount in the Earth's crust. It comprises about 26% by weight, and it's embedded in rocks, sand, and clay and soil. And we mentioned about this that the silicon is actually usually used a lot in technology environment as semiconductors manufacturing in electronics. So boron is also another semi-metallic element. And expressed at about 0.001% of Earth's crust by weight. So it means it has a really low amount in nature, but it has a really lightweight. It has a semiconducting property. It's very stiff, right, in fiber form. So also it can be used in as a nitride. Boron nitride can be used for the cutting tools, but those kind of cutting tools are usually very 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 expensive. All right, so that's about everything about metals and ceramics. Mainly, you need to understand the different properties of steels, irons, and also ceramics. And then remember those applications, how they are used in manufacturing processes or in manufactured products. These are some of the quiz questions. Also, these are the takeaways that you need to remember in this lecture. All right, that's it for today.